This is Unit 13, Nuclear Chemistry. Some atoms are unstable. So these atoms, they're going to break down or decay into more stable forms. There are three types of particles that are going to be produced by nuclear decay, and those are alpha, beta, and gamma. Radiation is the name that is given to all of these particles, or the energy that is given off by the atoms in the process of becoming more stable. Alpha decay is written by this Greek letter alpha. This is a helium nucleus, or alpha particles. And so they have 2 protons and 2 neutrons. So it is just the helium nucleus. The mass is 4 AMU. And the charge is a positive 2. These can be blocked by paper. Beta particles, the symbol is the Greek letter beta. These are beta particles, and they are electrons. They have a mass of less than 1, a charge of -1, and these can be blocked by metal foil. Gamma rays are the strongest type of radiation, and these are high energy photons. They have no mass and no charge, and they can be weakened but not completely stopped by lead or concrete. Positrons, those are beta plus, and these are the antimatter form of an electron. They also have a mass of less than 1 AMU, but this time they have a positive charge. And like beta, they can be stopped by metal shield or metal foil. The symbol for a neutron is a small n, and these are free neutrons. They have a mass of 1, but no charge, since neutrons have no charge. And these can be blocked by water or oil. So like I said, gamma rays can be weakened, but they can't be completely stopped by lead shielding. And this is what made the Hulk, gamma rays. So alpha rays can be stopped by paper. Beta and beta positive can both be stopped by metal foil, and gamma rays can be weakened but not completely stopped by lead. Alpha particles, they're going to emit alpha particles, that's the helium nucleus. They're going to change the mass of the atom by 4, so it will decrease by 4, and the atomic number is going to decrease by 2. Beta particles, they will not change the mass, but it will increase the atomic number by 1. Gamma particles, these are just energy, and so they are not going to change the mass or the atomic number. They're just releasing extra energy. Positrons, those are beta plus. They won't change the mass, but it will decrease the atomic number by 1. An electron capture, the particle is an X-ray photon. It doesn't change the mass, but again, the atomic number is going to decrease by 1 because that is an electron that is being absorbed into the nucleus. So in nuclear equations, the numbers of protons can change. So this means that the element that you have is going to change. So you have to keep track of the number of protons and neutrons in the reaction. When writing nuclear equations, we use the AZX notation. So A is the mass number, Z is the atomic number, or the number of protons, and X is the symbol for the element. So to write isotopes in AZX notation, we're going to use the mass. So that is the number after the hyphen. So uranium has a mass of 238. So 238 is on top. The atomic number is 92. And the symbol U. So carbon, the symbol is C. The atomic number is 6. And the mass number is 14. Try the next two on your own. So we can write and balance nuclear equations like chemical equations, but nuclear equations, the protons are going to change. So nuclear reactions are capable of transmutations, and that means that an atom's atomic number is changed. So when balancing nuclear equations, the reactions have to be balanced so both the upper and lower totals are constant from the reactants to the products. So we have the mass. We started out with 210 and 84 protons in the reactant side. So the product side has to have the same number for the mass and the same amount of protons total. So we're going to emit an alpha particle, which means that we're going to lose 2 protons. So we started with polonium, and it lost 2 protons. So the new element is lead, Pb. And 82 is the new atomic number. And our new mass number, it is decreased by 4. This is 206. In this reaction, the hydrogens are being fused together. And so we have 2 hydrogens that are fused, and 1 neutron is going to be emitted. So our new atomic number is 4, and that is beryllium, Be. And we have 8 total for our mass on our reactant side, but we have 1 neutron, so our mass is 7 for beryllium. We have to have 8 total. This next reaction, the gold is unchanged, so that tells you that it's gamma radiation that is emitted, since they are exactly the same from products to reactants. And so you just have to write gamma for the type of radiation that's emitted. Nuclear equations can also be written as sentences, and the words emit, decay, or ejects tells you that something was produced. So this means that the type of decay is going to be part of the product. So zinc 68 emits an alpha particle. 68 is the mass, and the atomic number is 30. So it emits an alpha particle. That means we have an alpha particle as the product. It has a mass of 4 and 2 protons. So that means our atomic number decreased by 2. So the new atomic number is 28, and that element is nickel. And our new mass is 64 because the mass decreased by 4. And the next problem, potassium 40, is formed by beta emission. So that means that potassium 40 and a beta particle are both going to be part of the products. So we have potassium 40. Potassium atomic number is 19. And we have our beta particle. Those are the products. So a beta particle means that the atomic number increased by 1. So our reactant will have 1 less. So the reactant would have an 18 as the atomic number, and that is argon. And with beta emissions, there's no change in mass. So the mass is still 40, and the atomic number is 18. So if the words capture or absorbed are used, then the radiation is going to be part of the reactant. So that means it'll be on the reactant side. So oxygen 16 absorbs a neutron. and the neutron is on the reactant side. This doesn't change the number of protons, so we still have oxygen, but the mass has gone up by 1. So oxygen 17. In this next problem, lithium captures an electron. And this isn't like bonding. It's not getting a negative charge. It is actually an electron getting absorbed into the nucleus of the atom. And so it is changing one of the protons into a neutron. So we have 6 for our mass, 3 for our atomic number, and it's going to absorb an electron. So our atomic number is going to decrease by 1. So we have helium. So the product is helium-6. So in the next problem, beryllium is absorbing a neutron and emitting a beta particle at the same time. So the neutron, since it's absorbed, is part of the reactant side, and the beta particle will be part of the product side. So a beta particle tells us that we are going to lose, our atomic number is going to increase by 1. So we have 5. Our mass also increased by 1 because of the neutron. And so we have boron 5, or boron 11. So radioisotopes, these are unstable isotopes, and they typically undergo more than one type of decay while they're trying to become stable. So these steps are called a radioactive decay series. Large elements, they're going to lose mass by emitting alpha particles. They lose energy through gamma radiation, and they're going to balance their protons and neutrons, or the proton-neutron ratio, by emitting beta particles. So sequences, they can be balanced the same way as other nuclear equations. So here's a sequence for thorium. It starts out with an alpha decay, then it has 2 beta, then it has 4 different alpha decays, then there's 2 different options of what it can do, but you still end up with the same product at the end of the decay series. So it can either have a beta and an alpha decay and another beta, or 2 betas and then an alpha decay. So here's a series with uranium-238. It's going to undergo the following series. So we start with uranium-238. Its atomic number is 92. And we can count up the number of alpha decay, there are 6 alpha particles that are going to be emitted and 2 beta particles. The alpha particles, they're going to decrease the atomic number by 12. And the beta particles are going to increase it by 2. So our final atomic number will be 82, which is lead. And our mass number decreased by 24, and so it is 214. So in the next equation, polonium is going to absorb 2 neutrons and then undergo alpha-beta decay. So the 2 neutrons, those are going to be part of our reactant side. And we have 2 alpha particles that are emitted and 1 beta particle.
So we look in polonium, lost 4 protons and then gained 1. And so our new element is Pa, and its atomic number is 91. And the new mass number, since it lost 4, or it lost 8, but gained 2, the new mass number is 233. All elements are created in a process known as nucleosynthesis, and this occurs in the cores of stars. And the atoms are exposed to incredible amounts of heat and pressure. So smaller atoms are fused together. This is called nuclear fusion. And fusion means 2 small atoms being put together. Our sun is a dwarf star, and so it's not able to fuse any elements that are larger than carbon, but very large stars, massive stars, can fuse carbon and even larger elements. So fusion is going to produce heat, meaning it's exothermic, whenever it's producing more stable elements. Iron 56 has the most stable nucleus. So whenever it's producing elements that are smaller than iron 56, it is exothermic, but whenever it's fusing elements that are larger than iron 56, this is going to require energy. So it's endothermic. Massive stars will die very quickly once they begin to fuse iron. The expansion is going to stop, and the star begins to collapse inward. And this is going to be followed by a large explosion called a supernova. And this explosion is what's going to produce all of the elements that are larger than iron. So check out the link to the video about the supernova. Fission and fusion are two common nuclear reactions, and these both occur naturally. Fission is going to occur in larger elements, and this is when an atom is split into smaller atoms and particles. Fusion also occurs naturally in a star's core. This forms larger elements from small elements like hydrogen and helium. And hydrogen bombs and nuclear bombs are fueled by fusion reactions. So in chemical reactions, the mass of the reactant is always the same as in the products because this is the conservation of mass. However, in fission and fusion reactions, the conservation of mass isn't completely obeyed. So small amounts of mass are going to be lost in fission and fusion reactions. This difference in the mass is known as the mass defect. Nucleons are the components of the nucleus, and so those are protons and neutrons. The missing mass is going to be converted into energy. So we're going to use the equation E equals mc squared. Since c is the speed of light and it's squared, just a tiny amount of mass is going to produce a massive amount of energy. C, if you remember, is 3.00 times 10 to the 8th meters per second. So let's take a look at this equation. E is energy, and it's measured in joules. M is the mass in kilograms, and C is the speed of light, which is 3.00 times 10 to the 8th meters per second. How much energy is going to be produced if 1 kilogram is converted into energy? So energy equals mass, which is 1 kilogram, times the speed of light, squared. So this gives us our energy as 9 times 10 to the 16th joules. Since elements with a mass of 60 are the most stable, larger elements tend to fragment into smaller elements. This is called nuclear fission. Fission produces a large amount of energy and is what's used in nuclear power plants. Nuclear power supplies about 11% of the world's electricity. In a nuclear power plant, energy is produced by the fission of elements. This is usually uranium-235. In each fission of uranium-235, additional neutrons are released. Each of the 2 neutrons that are released can cause an additional reaction. This process of one reaction initiating the next reaction is a chain reaction. An atomic bomb is an example of an uncontrolled chain reaction. There must be enough material to sustain a chain reaction. This is called the critical mass. When the critical mass is present, the neutrons from one reaction cause the next reaction. So one uranium atom is going to produce two neutrons, and those two neutrons will collide with two other uranium atoms, which will then produce two neutrons, which can go on to collide with two more uranium atoms.
In a nuclear reactor, the fuel rods are inserted into the reactor, and they're separated by a few centimeters of water or of graphite. The water acts as a moderator, so it's going to slow down the neutrons and makes fission more likely whenever a neutron collides with a uranium atom. The control rods in a nuclear reactor regulate the neutrons and can control the collisions by sliding between the fuel rods and absorbing neutrons. When the control rods are partially removed, fission increases. The heat from the reaction is used to heat water to make steam. The steam spins a turbine, which spins a generator to make electrical energy. By moving the control rods, the rate of the fission can be increased or decreased. Nuclear chemistry is also used for radiochemical dating. Radioactive decay rates are measured in half-lives. A half-life is the amount of time needed for half of a substance to undergo radioactive decay. So in this example, the mineral deposit at the very top has 16 atoms that are radioactive. After one half-life, it only has 8 radioactive atoms left. After the second half-life, it has 4, and after the third, it has 2. So after each half-life, 1/2 of the substance has decayed. Here's an example. Strontium-90 undergoes beta decay. So to determine the remaining amount of the radioactive element, use the equation N equals N sub naught times 1/2 small n. N is the remaining amount, N sub naught is the initial, and small n is the number of half-lives.
So whenever you begin, the number of years that have passed are 0, and the initial sample had 10 grams of strontium-90. So the equation is N equals 10 times 1/2 to the 0 power. Strontium has a half-life of 29 years, so after one half-life, 29 years have passed, and there are 5 grams of strontium-90 left. After 2 half-lives, 58 years, there will be 2.5 grams left. After 3 half-lives, 1.25 grams. After 4 half-lives, 116 years, there are only 0.6 grams left. Each radioactive isotope has its own half-life. Some of them are billions of years, and others are only millionths of a second. Polonium-214 has a very short half-life, 163.7 microseconds. Cobalt-60 has a half-life of 5.272 years. Carbon-14, which is used as carbon dating, has a half-life of 5,730 years. Iodine-131 is used in treating thyroid cancer, and this has a half-life of 8.02 days. And uranium-238 has a half-life of 4.46 billion years. Half-lives are used to determine the age of objects by measuring the amount of radioactive isotopes that are left in the object. This is called radiochemical dating. Carbon dating is used to determine the age of things that were once alive. This uses carbon-14, which has a half-life of 5,730 years. Carbon-14 is formed by cosmic rays in the atmosphere. The carbon-14 can then mix with carbon-12 and carbon-13 in the biosphere. Plants use all 3 types of carbon in photosynthesis. When the animals eat the plants, the carbon becomes part of that animal. Because the plants and animals are constantly taking in carbon, the ratio of carbon-12, 13, and 14 is about the same as what's found in the atmosphere. When that animal or plant dies, it can no longer take in any more carbon, and carbon-14 begins to decay into nitrogen-14 by beta decay. By measuring the ratio of carbon-14 to 12 and 13, the scientists can determine the age of an object. This is accurate for objects up to about 45,000 years. Uranium-238 can also be used to date objects that are older than 45,000 years, and it's estimated that our solar system is about 4.6 billion years old by dating meteors. Other uses of nuclear chemistry include medicine. Technetium-99 is used in imaging. Iodine-131 is used to treat thyroid cancer, and some hospitals even use cobalt-60, which produces gamma rays, to sterilize equipment. Nuclear chemistry is also used in weapons, like the weapons used in World War II. It's also used in transportations. There are nuclear-powered ships like submarines, and radioisotope thermal generators are used on different space probes. And the Curiosity Mars rover is also powered by RTGs. Nuclear chemistry is used in agriculture with plant mutation breeding. Plants are exposed to gamma rays, which cause mutations, and then those plants are planted and grown to produce different varieties. It can also be used in fertilizers and insect control. Nuclear chemistry is used in consumer products like watches and clocks, and also smoke alarms. A radioactive isotope is inside of the smoke alarm, which causes a constant amount of alpha radiation or alpha particles to be produced. And when the smoke enters the alarm, the alpha particles are disrupted, and that causes the alarm to sound. It's also used in industry to monitor fluid flow, filtrations, and to detect leaks.